Okay, in today's video, we're going to calculate the tension and acceleration in a pulley system problem. Specifically, we're looking at an Atwood machine. I'm not a trained physics teacher. I'm definitely not going to use the best terminology, um, but I am going to do my best to explain it accurately and simply. To help me with that, I have brought up a few notes that you might already have, or maybe you want to make notes of them for yourself. Just what an Atwood machine is, a couple of key notes about it, like if there's a difference in weights between the two objects attached on either end of the rope, then the system will accelerate. If the two masses are identical, there's no acceleration. And I also have down here these two super very important formulas. Um, so for the lighter mass, we have tension minus mass time, the first mass times gravity equals the first mass times acceleration. And then for the heavier one, so the second mass times gravity minus tension is equal to the second mass times acceleration. We can use these to calculate for acceleration. And the reason we can do that is because the tension in this system is the same throughout the rope. You're not going to have more tension on the left side of the rope and less on the right side. It is going to be the same throughout. So let's let's go through it. I believe the question that we had was, let's say, here's your ceiling, here's the pulley. Let's make ourselves a rope. Okay, there's our rope. And we've got two things attached. I'm gonna make a call this mass one, and I'm gonna call the other one mass two. Very, very creative, I know. Mass two. And we're gonna say that we're gonna say mass two is, I think it was 28 kilograms in the problem that was sent over. And in mass one, I believe it was 15. Okay, so because these two masses are not identical, there is going to be acceleration. There is going to be movement in this system. This mass is bigger, so we're going to be moving in this direction. Mass one is going to be moving upwards. Mass two is going to be moving downwards, because that is just how it works when you have one thing that's heavier than another. So let's go ahead and set up a couple things. I'm actually going to, you can jump straight into these two formulas right here, and if you'd like to, by all means, go ahead. I personally like to start with this one just because it's the most basic formula, and I like to start basic and have it make sense to me. So that's what I'm going to do in this video. But you can go ahead and try out these two and jump forward if you'd like. But the basic formula, when we're dealing with tension, tension equals the mass times gravity, or the acceleration due to gravity, and then the acceleration of the system itself. Now, you and I are going to solve specifically for A, acceleration, and then we'll solve for tension after that. But remember how I said that the tension throughout the entire rope or chain or whatever it is would be identical? Yeah? So this means if I took this tension for mass 1, gravity and acceleration, and if I took the tension mass 2, gravity and acceleration, whoops, these two tensions, the green one and the purple one, have to be identical. So if those are identical, then I can also set these two expressions as equal to each other because they must also match up. They must balance out. And so that is what I'm going to do. I'm going to scoot right over here, and I'm going to say mass 1 times gravity and acceleration is equal to mass 2, gravity, acceleration. And then I'm going to go ahead and I'm going to fill in what I know. So, well, I just heard my cat meowing. He thinks I'm done for the day. Poor little guy. Okay. Sorry about that. We're going to fill in what we know. We know, for example, mass 1. We know that's the 15, right? We know mass 2 is 28, right? Okay. Let me plug in the parentheses and the equals there, sorry. We also know acceleration due to gravity. Because we're talking about kilograms here, we're using the SI unit, so acceleration due to gravity is about 9. Uh-oh. Oh no. What's this? My screen's just having a freak out. Okay, we're good. We're back. We're fine. 15 times A, 15A. And on the other side, I'm going to distribute this to 28. 28 times 9.8. Grab my calculator. 28 times 9.8 is 274.4. And I'm going to continue to distribute. And I'm going to do 28 times negative A, which is negative 28A. And the whole thing we're doing here is we're solving for the acceleration of the system. How fast are these two masses moving over that pulley? So I need to solve for A. And the first thing I'm going to do is I'm going to add 28A to both sides of this equation. And over here I've got 15 plus 28. And I am using the calculator to get 43. Okay, and I'll now drop down everything I haven't messed with. That's still there, that's still there, that's still there. Okay. Next up, I'm going to subtract 147 from both sides. Okay. So we're going to have to do 147 minus 147. That just disappears. That's the whole point. On the other side, 274.4 minus 147 is 127.4. And again, I'm going to carry down what I haven't dealt with yet. And really, I just have the 43A equals 127.4. The very last step here, before rounding and writing out my final answer, is dividing both sides by 43. Can you hear my cat meowing? Is it coming up on the microphone? Because, oh my gosh, he's going at it. All right, divide both sides by 43. That's just going to be 43 divided by 43 cancels. Hooray, A is by itself. That's what I wanted. And on this side, again, I'm grabbing my calculator off screen. I'm doing 127.4 divided by 43. And I'm going to get a ridiculously long number, 2.96279, blah, 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 blah. I'm going to go ahead and round this to, I'm going to give myself 3 significant figures, and I'm going to get 2.96. That's acceleration, and it is in meters per second squared. So this would be the acceleration of the system. All right, so that was our first question. Now, there are other ways to go about this. I believe, let me see. Like I said, I jumped into the most basic equation, and I wanted to think for myself, okay, am I adding in or am I subtracting in? You know, which one's working harder? If that's a little too uncomfortable for you, just write these down. Write these down. The lighter mass is this formula, the heavier mass is this formula, and it can be a little more complicated. If you'd like to see a video of how to use just this and not the way that I did it, just let me know in the comments and I will happily make a video with the same problem, but using those formulas instead. It'll still work, just look a little different. So it's up to you. But we do now have the acceleration of the system. Beautiful. We now need to find the tension that is in the rope, or the cord, or whatever it is. And we did say the tension was equal throughout. So that should help us. That should help us a little bit. All right, let me get set up and we will answer the next question. My computer is having a spaz attack. Okay, we're back. I had to pause to feed my cat so he'd stop yelling at me. We'll see if it works. So we calculated the acceleration, 2.96 meters per second, and you know what we can do? We can solve this in super, super complicated ways, or if we wanted to solve for tension, we can just plug acceleration into either one of these formulas. Let me show you. Let me show you what I mean. Let's just kind of reverse engineer it. Let's take the first one. Now, I did round, so technically the most correct answer would be if I plugged in the acceleration that I had gotten before I rounded. Remember, I got like 2.96279, blah, 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 and I did round to 2.96. If I were to use the full number for this next step, I would get a more accurate answer, and your instructor may want you to be more accurate when doing this part. So, you know what, let's give it a shot. Let me plug in the whole smegging thing, and we'll give it a go. So, we're going to say that the tension attached to the green box is equal to the green mass, it's 15, and the gravity, or the acceleration due to gravity, 9.8. And we calculated our acceleration of the system as that 2.96, what was it? Something, 279. Let's use that number. 279. Go ahead and throw this into your calculator. 15 times, parentheses, 9.8 plus 2.9627. And see what you get. I'm going to do it too. I'm going to get 191.53185, blah, 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 blah. That right there would be the tension in the entire thing. I know we only use the green side, but because the tension in the rope that's attached to the green box is the same rope that's attached to the purpley box, tension is the same. We can verify this by using the second formula. We can take the purple one, which had a mass of 28. Acceleration was 9.8, and this one we subtracted the acceleration of the system because this box, the heavier box, was moving downwards. So subtract the 2.9679. No, I forgot a 2. Totally. Go ahead and plug that in. And again, I did round even the 2.96. Oh, did I type that wrong? 2.962. Oh, I did. Hold, please. Okay, hopefully you were doing this along with me and you were like, hey, you wrote the wrong number down. Because I did. I was off by a couple decimals. Let me fix that. I sincerely apologize if I gave you a little heart attack there. 2.96279. Let me fix that. Up here, it's actually 1.91441. That's what we're looking for. Okay, beautiful. Now go ahead and put this purpley one in there, and we should get the same answer because tension is equal throughout the entire rope in this pulley system. So 28 times the difference of 9.8 and 2.7, no, 2.9627, and we should get almost the exact same thing. Oops. My goodness, my head is just not on straight today, is it now? Tension equals 191.441. This one's 188. Again, I did, even though I wrote down as much of this number as I could, the acceleration that we calculated in the first step is not, that's not the exact answer. My calculator only showed me that many decimals. Your calculator might have showed you more. But either way, we find the tension in the system is 191.4. That would be if we rounded it to have 4 significant figures. I don't know if the instructions, let me take a peek at the paper. Does it say if we want a certain number of significant figures? No, it doesn't. And based on the paper that I was sent over by the fabulous physics student I'm working with at the moment, it doesn't look like I can't figure out what the rules are that are being employed for significant figures. What the teacher has done is rounded this to tension, oops, wrong button, of 191.4 newtons. So it has a completely different number of significant figures than the acceleration did, oops, or the initial masses. So I'm not really sure. But I feel pretty comfy saying that if you showed your work like we have here, and again, I don't think I mentioned it, but this document will be available for download if you're interested. The link will be in the description. I'll try to clean it up a little bit if I can, but this will be available. And if you show your work on your test or your homework, I would assume that the instructor would be like, okay, they know what they're doing, and you'd be in pretty good shape. So that's it for this question. If we have this particular system with these weights, these masses, we can find the acceleration, we can find the total tension, and that's it. So that's, I'm gonna go ahead and stop talking now because I've done it a lot, and I will make that document available for download, and I will put links in the description to anything else that might be helpful, and you can always leave questions in the comments. Please feel free.